Hello pre-calculus class. For today's classwork, we will be graphing out polar equations. Before we begin, again, please be aware of the four equations we need to become familiar with in order to convert polar equations to its rectangular equation equivalent. For our first example, we will graph it both in its polar equation and rectangular equation, just to show you that one graph will be equivalent with the other graph, so you only need to graph from its polar equation form. So for our first polar equation, we have r equals 2. To graph this, just keep in mind that polar coordinates are always in the form of radius comma theta. We are given a radius of 2, but not given what the theta must be. So we can actually plug in the theta. Let's use 0, pi over 2, and pi. Once we plug in those 3 points, we can already assume the pattern of the other points. It's going to give me a circle of radius 2. Now intuitively, that seems to match this equation since it says r equals 2. If I were to convert this into its rectangular form using this equation, r squared is going to be x squared plus y squared, and 2 squared is going to be 4, but I'm just going to leave it in 2 squared because this follows this format, x minus h squared plus y minus k squared equals r squared. Now we learned this in geometry as well as in algebra 2 as the equation of a circle, and this indicates that it's a radius of 2 with a center of 0. So a center of 0, a radius of 2, and a circle completed. So as you can see, whether you graph it in the polar equation or rectangular equation, you would end up with the same graph. So going forward, we will just graph it from its polar equation. Let's look at the second example. This time theta equals pi over 2. Again, polar coordinates take the form of radius comma theta. This time the radius is not given, so we can fill in sample radiuses, or radii. 0, 1, 2, let's say. So radius of 0 at pi over 2 would be this dot at the origin. 1 comma pi over 2 would be a radius of 1 at pi over 2, 2 comma pi over 2, and you can already see that this would create a vertical line of the form x equals 0. And again, you could have converted this to its rectangular equation and then graphed it out, or we could have just graphed it out from its polar equation form. Now for the next two examples, I'm going to already introduce the very last page of your reading in this section. If you go to page 560 function gallery, they already give you the forms of the polar equations in their graphs. So if I have a polar equation of this form, which we will read about in one of the examples, or this form, which we are about to do, we can already anticipate the shape it's going to create. So on your quiz, I would like you to already know what shape you're going to graph before graphing it. But of course, I would like you to show your work. And how would you show your work? Well, in the form I'm about to show you. In your reading, they have a table of values to help introduce why the shape looks as it is. And they use 2 rows. For our purposes, though, I'm going to use 3 rows to help you see the middle step in between the calculations. So here we have r equals 2 sine theta. So r is simply going to be 2 times whatever sine theta will give me. So that's what I'm going to calculate beforehand. So sine theta, what is sine of 0 degrees? Well, sine of 0 degrees is 0. Sine of 30 degrees, 1 over 2, and now we can fill in the rest of this table. Once we're done, we're going to find out its radius by multiplying 2 times the sine theta, which was this row here. So 0 times 2 is 0, and so forth. Now keep in mind when we're graphing this, we are already expecting a certain shape. We are expecting, and I'm just going to scroll back down to the function gallery, this shape right here, because our equation takes the form of r equals a sine theta. So we're already expecting a circle that looks like this. So in our work, we simply have to show where we got some of the points. So for example, 0, 0. All right. Oops. 1, 30 degrees. 2, 90 degrees. 1, 150 degrees. And 180, 0 is back to the origin. So we can see why the pattern repeats itself to create a circle over and over and over again. So if we fill in the other points, square root 2, 45 degrees, and square root 3, 60 degrees, we can see that we will indeed create a circle. Now it looks a bit off because the distance between here isn't actually going to be 15 degrees. Oops. So it's not to scale in this current visual, but we will be creating a full circle, as you can see here. And if we were to follow up on the reading, where they graphed out r equals 2 cosine theta and did the table of values as they have done, we would also create this circle. And we would confirm that by looking at the function gallery, again on page 560, to see that it took this form, since we have r equals a cosine theta. And we do. The only difference being that this circle is on top of the x-axis, this form being on the right of the y-axis. So hopefully the graphing part won't be too difficult. It's just for us to know where the values came from. So I'm going to end with one more example here. The only difference being that there's a 2 inside. So before I begin, I'm going to already try to anticipate the shape it's going to be by looking at the function gallery. And we will find its equivalent right here. Now I know it says cosine, but it'll show very similar patterns, as you'll soon see. So r equals 2 sine 2 theta. So we're looking for a flowery shape in the end. All right, let's plug in some values. This time though, just keep in mind that they are looking for 2 theta. So 2 theta in this case is going to be 0. This is going to be 60 degrees. This is going to be 90 degrees, and so forth. So when we're looking for sine value, we're not looking for sine theta, but rather sine 2 theta. So sine 2 theta here is sine of 0 degrees, which is 0. Sine of theta is 30 degrees, but sine of 2 theta is going to be 60 degrees, so we get square root 3 over 2. Sine of 90 degrees is going to be 1. Sine of 120 degrees is going to be square root 3 over 2. And we can fill in the values accordingly. And so r would be 2 times the sine 2 theta. So we get the following values. So if we were to graph this out, just keep in mind that our original theta was 0, 30 degrees, and 45 degrees, and not the 2 theta that we calculated with. So 0, 0 is going to be this dot in the origin. Square root 3, 30 degrees. Square root 3 is between square root 1, which is 1, and square root 4, which is 2. And it's going to be 30 degrees. So roughly here. And 2, 45 degrees. And square root 3, 60 degrees. And from that, we can get this kind of pattern. And if we continue that, we will get a flowery shape. And so I'm going to just cut the time short by showing you what it'll look like. So we just graphed out the top right petal here, and if we were to continue this, we would get a flower with 4 petals. Now just to show you that we will still get the petals whether or not we have 2, 3, or 4 inside, just going to show you what the other ones look like. So r equals 2 sine of 3 theta looks like this. And a 4 theta looks like this. And 5 theta looks like this. So you can already confirm your work by looking at its equivalent form, but please show your work using the table. Lastly, I'd like you to see the cosine equivalent. So 2 cosine 2 theta, and then 2 cosine 3 theta, oops, and then 2 cosine 4 theta, and 2 cosine 5 theta. So you can see that they're exactly the same, but they're tilted. All right, good luck.